Hello, my people. Hope we're doing well. This is video 3 for sine and cosine graph transformations. In the first video, I went ahead and constructed the sine and cosine graphs again for you. In video 2, we did the first two of these, right? This was video 2. And here we're going to do these last two, number 3 and number 6. Okay? Let's go ahead and get started on these. Now, it says h of x is equal to 3/2 sine of 4/3 x minus pi. Now, whenever you are factoring a fraction or a negative out, obviously that's going to be you want to take extra care in doing that, right? Like I've said before, because you're sort of undistributing, and sometimes multiplication and division when we're dealing with fractions gets a little messed up in our head. But let's go ahead and think about it like this. If I want to bring 4/3 out of both terms, let's go ahead and call this 12/12 pi. And here's why I want to do it. If I think about it as 12/12, and I didn't just pick 12/12 out of a hat, it's obviously the least common multiple of 4 and 3. I want you to think about it like this. Right? 12/12 can be pulled apart into 4/3 times 3/4, which gives us sine of 4/3 x minus 3/4 pi, or 3 pi over 4, right? Or, if you don't want to think about it like that, you can think about it like this. I keep telling you that factoring is a form of division. And if I'm factoring 4/3 out, I am dividing by 4/3. I'm dividing both terms, or what should be left in both terms, by 4/3. So if I divide by 4/3, I'm dividing by a fraction, which is the same as multiplying by its reciprocal, 3/4. And there you go, okay? So we want to rewrite this as 3/2 sine of 4/3 x minus 3 pi over 4. And this tells us that we want to move it to the right, 3 pi over 4. Okay, that tells us that we want to vertically shrink by 3/4, right? And we shrink because that's a number, it has a magnitude greater than 1. And then, horizontal. Okay, and vertically stretch by 3/2. Okay, now the vertical shrink by 3/4, remember that comes about because the original period is 2 pi and you're dividing by 4/3, which is 2 pi times 3/4, which is going to be 3 pi over 2. Your new period is 3 pi over 2. Okay, well, if I'm shifting by 3 pi over 4 and my period is 3 pi over 2, I think it's probably best that I don't scale this with pi right here. Instead, let's scale it with pi right here, so it's broken up into 4 pieces rather than 3. And that's what I mean by, take a look at the function and the transformations and actually think through the implications of exactly what it is that you have there before you start setting your scale. Now, I've done this according to the way that I usually do it, with every 4 boxes being 1 unit, because you're dealing with 3/2, 1.5, right? And that's going with it broken up into each unit broken up into an even number of boxes. It's going to be easier to show 1.5 stretch on the Cartesian plane. Well, let's go ahead and draw our parent function. Right? We have goes from here No, it goes to pi over 2, and then back down here. Sorry, let's ignore that. And what we have here is... sorry about that. I'll be done in just a second. I want to make sure that the graph is actually somewhat accurate. I've got to turn the piece of paper in order to do that sometimes. Okay. There is our parent function, right? It's got a period of 2 pi. It goes up to positive 1, has minimums at negative 1. And now I need to transform it. Let's go ahead and start by transforming some of these and then sort of extrapolating from there what the other points are based upon our symmetry and our period. So we're going to take 0, 0. We're going to move to the right 3/4. Then we're going to horizontally shrink it. Well, it's at the 0 point, right? This is our new 0. This is our x is equal to c point. And you can't stretch or shrink or reflect 0, so it just stays. It's also on the x-axis, and you can't vertically stretch that either. So let's go ahead and just, boom, there's our new point of intersection. Now, I know that I have a new period of 3 pi over 2, which means, and every 2 boxes is pi over 2. So pi over 2, 2 pi over 2, 3 pi over 2, that right there is a full period. But I know that my points of intersection happen twice every period. And so they happen like that. Okay? Okay, well, let's go ahead and let's transform this maximum right here. I see the fact that it is at pi over 2. And if each one of these boxes is pi over 4, if I move it to the right 3 pi over 4, I just move to the right 3 boxes. 1, 2, 3. Fantastic. Now, it is 2 units away from our new 0 point, right? There's our new 0 point, and it's sitting right here. It has moved over 1, 2, 3, and now I need to stretch it I need to shrink it by 3/4, okay? If 2 boxes is 4/4, then 1.5 boxes is 3/4, and then I need to vertically stretch it. Sorry, I forgot about vertically stretching. And there's our new maximum. Okay. Well, I know that each maximum happens once every period. So I need to basically pop over here 3 pi over 2. And then pop over here another 3 pi over 2. And I know my minimums are going to be the same distance away from the axis of oscillation, but they're just going to be in between the opposing, like the other 2 points of intersection. And so I get those. Okay, well, basically what happens here is at pi over 4, you have root 2 over 2. And we got pretty close to doing that right there because it's 0.707, and that means it's just a little bit under 0.75, which is 3/4. Let's go ahead and let's move that 1, 2, 3 units, okay? And now that is just pi over 4 away from that new axis of that new 0 point, and then 3/4 of that is here. See, this is just getting a little bit dicey. And then we need to multiply it by 3/2, okay? Well, it needs to go like vertically stretched by 3/2. Well, 3/2, that makes it kind of difficult. Let's actually skip that. Now, sine at pi over 3 is 1/2, and we almost hit that exactly. It should be right about there. Let's actually talk about that one right there. Because pi over 3 is 1/3 of the way to the maximum in terms of x distance, right? 1/3 of the way to the maximum and halfway to the peak. So 1/3 of the way and then 1/2 to the peak. And here's what you get. You get those points right there. Okay. And here's on problems like this where those points are a little bit difficult to discern from the from the parent function, but also hard to transform because you're dealing with fractions of fractions when you start sort of transforming them. it's those points that actually are really, really helpful. It's really helpful to use your analytic and inverse trig skills in order to find those, okay? And this is what the graph looks like. Now, of course, the more fractions and the more negatives you have in the transformation that's given, the harder it's going to be. The more you're forced to use a scale that accommodates pi over 4, the more difficult it's going to be, right? Because the only rational value that goes around the unit circle, with the exception, of course, of the ones on the axes, is the 1/2 ratio. The other two are root 2 over 2, irrational, root 3 over 2, irrational. That's one of the reasons why, if you can get away with it, try and scale according to pi over 3, because those are just going to be much easier values to transform. But it's not like we didn't have, not like we couldn't do it here. Now, these, obviously, the points that I wound up plotting here, 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 and here are at 3/4. What do you say we, just for giggles, ask this function, say, Mr. Function, let's see if I got those where they should be. I want to know, when are your outputs 3/4? Now here's the thing. That's neither a maximum nor a minimum. It's not an x-intercept. It's just a point that I'm wondering if I did the transformation correctly. And that's perfectly a legitimate question to ask the function, especially if you're just trying to figure out if you did things correctly. Okay, well, if I do it that way, then basically what's going on here is I divide both sides by 3/2. Well, 3/2 is twice the size of 3/4, so that gives me when is sine equal to 1/2. Well, I have a little more room here, so I'm not going to put them on top of each other. I know when sine is 1/2. Sine is 1/2 when the angle measurement is pi over 6, or when the angle measurement is 5 pi over 6. And then, of course, plus 2 pi n, all of the coterminals, right? Okay, well, let's go ahead and add pi to both sides. That gives me 7 pi over 6 plus 2 pi n. And 4/3 x is equal to, well, that's going to give me 11 pi over 6 plus 2 pi n. And now I need to multiply both sides by 3/4. If I multiply this by 3/4, that's 7 pi over 6, remember that I need to distribute it because it impacts the period, and this, of course, is representative of that period. And therefore, what I have here is I'm going to have 21 over 24, or, we're going to go ahead and reduce. That's 7 pi over 8 plus, and here, over 3 pi over 2n. And of course, if 2 pi was the original period, you already know that 3 pi over 2 is the new one. So I should have an output of 3/4 where x is 7 pi over 8 plus 3 pi n. Now 7 pi over 8 is not a unit circle value, but it will be easy to read off of our graph because our graph was scaled to accommodate pi over 4. So I really don't care whether it's a unit circle value. Let's go ahead and do this one. We're going to go ahead and multiply both sides, and remember that you have to, of course, again, distribute, right? Now this is 1 and 2, and so that winds up being 11 pi over 8 plus 3 pi over 2n. So we should get values of positive 3/4 at 7 pi over 8 and 11 pi over 8 and every period after that. Okay, 7 pi over 8, right? 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8, 5, 6, 7 pi over 8 at 3/4. 8 pi over 8, 9 pi over 8, 10 pi over 8, 11 pi over 8, again. 3/4. Okay. So in terms of doing those, plotting those points with respect to just the transformation and what I could tell right here, that is confirmed by my analytic work that I've done over here. And all I really did was just ask the function a question and then use my analytic work and solving for it, including my inverse trig operation, in order to confirm that. Okay. Now, let's go ahead and do this last transformation problem, and this will be tons of fun. This is called h of x is equal to -1/2 cosine of pi minus 2x minus 1. Now, those of you who know that cosine is even should basically already know that when we're dealing with that, that is the same thing as 2x minus pi, right? Because when you flip a difference, it becomes its negative. Well, if cosine is an even function, that negative gives you pi minus 2x and pi minus 2x and 2x minus pi give you the same output, and therefore they are equal. The last thing that needs to happen here is I just need to factor out that b value, and so I have x minus pi over 2 minus 1. Now, the difficulty arises because there are 5 transformations on this function. Okay, it moves to the right, pi over 2. We have a horizontal shrink of 1/2, which means I now have a period equal to pi. I have an x-axis reflection and a vertical shrink of 1/2, and it moves down 1. That is a whole lot that is going on, and the thing is that none of it is particularly difficult. It's just a little bit, cumbersome. You just meh, right? Okay, so I don't have any reason to need to accommodate pi over 4. So in my usual fashion, I'm going to go ahead and scale it for pi over 3. I know that although I shift down 1, right, it's not going to risk going off the Cartesian plane because I'm not vertically stretching, I'm vertically shrinking, okay? And so, again, I'm going to use my normal scale of 4 boxes is equal to 1 unit, because I know that basically it's going to be oscillating around y is equal to -1, but it's only going to go half a unit up and half a unit down as it oscillates. Alrighty, let's go ahead and do the parent function really quickly. We know that it starts at 0, 1, goes to pi over 2, 0, goes to pi 1, and then continues in that way all the way through. Okay, we know that here it's at 1/2. Okay, now let's go ahead and just transform some representative points, and then again, as always, we'll extrapolate from there. Let's take that point right here, and let's move it over pi over 2. Then we need to horizontally shrink it. Well, we've just redefined where our 0 point is, right? Our new 0 point is right here, and you can't shrink 0. So in terms of that point, as we're trying to transform it, stays where it is. Then we're going to x-axis reflect it. Then we're going to vertically shrink it by 1/2, and then we're going to move it down 1. And there we go. Now remember that it was a maximum, but because of the reflection, it's going to be a minimum value for this new graph. And those minimum values occur once per period. Well, since the period is pi, I know that I can just move over pi and plot another one. And then move over pi and plot another one. And then move to the left pi and plot another one. And move to the left pi and plot another one, and so on and so forth. Now, we also, and we could have done this earlier, but it's sort of getting to the point where it's necessary. Let's go ahead and draw our axis of oscillation at our y is equal to -1. And let's go ahead and transform this point right here. This point right here moves over pi over 2. Now, it shrinks back to roughly right about here. There is no x-axis reflection. There is no vertical shrink. It simply moves down 1 and becomes there. Now remember that the minimums, halfway in between them is going to be the maximum, which goes up, right? So halfway in between, up. Halfway in between, up. Halfway in between, up. Halfway in between, up. And of course this one sits sort of right here, and that's going to... And so we have to... I mean, I guess we could have scaled this so it accommodates pi over 4, because that would certainly be helpful. But I just find that to be annoying. And so basically we can sort of ish this as best we can. And we get those points of intersection like that. And our graph looks something like this. Okay, there is our transform graph. Now, let's say just for giggles, somebody says, hey, use your analytic and inverse trig skills to show me where the x-intercepts are. And you're saying to yourself, there are no x-intercepts. And they say, well, I tell you what, why don't you show that to me analytically, okay? And again, I'm going to do it I'm going to use my even function, the symmetry, to transform pi minus 2x into 2x minus pi. And you say, okay, well, let's just go ahead and set that equal to 0, because isn't that the question you want to ask? You're saying, Mr. Function, when are your outputs 0? Okay, well, let's go ahead and use our algebra skills. We'll push 1 to the other side, and then what we'll do is we'll divide by -1/2, and I get O. There's a problem there. And that problem is the analytic indication that there are no x-intercepts. Because cosine oscillates, I don't care what the angle measurement expression is, cosine oscillates between -1 and 1. Cosine can't have a ratio of -2, and therefore there are no solutions. Okay? Now, like I said, all of this stuff with the analytic and the inverse trig operation, I'm trying to sort of introduce this to you. It's not on this quiz that you'll have over this weekend. It will likely be on the test that's over the first 3 weeks. But we'll continue to go over it. We'll go over it as we do the graphs of the other 4 trig functions. We'll go over it as I introduce inverse trig to you, both as an operation and as a function in 4.7, which will be starting next Wednesday. And from there, it'll be a little bit more natural that it sort of folds in with the rest of it. I hope that has been helpful, guys, in both in terms of the introduction to the inverse trig as an operation, which we've touched on briefly before, but also in terms of how to make sense out of these transformations as they relate to sine and cosine graphs. And as I said in class, these actually, once you understand the shape and the periodic nature and the symmetry of these sine and cosine graphs, they should be so much easier than the exponential and logarithmic ones, because those don't have any symmetry. And that's where the difficulty lies for those. These, once you plot one point, it corresponds to, to each and every period before and after that, which winds up being really, really helpful. As always, if you have any further questions about any of this, do shoot me a message. Have a good weekend. Bye.